Welcome back everybody. This next video lesson, we're going to cover two learning objectives. The first one is I can describe isotopes and use them to calculate atomic mass. And the other one is I can determine atomic mass, mass number, number of neutrons, number of protons, and number of electrons for an atom. Now let's start with isotopes. Now what is an isotope? Besides the baseball team on The Simpsons, the Springfield Isotopes. Isotopes are atoms that are identical in atomic numbers, but have a different mass number. Well, what is mass number? Mass number is the sum of the protons plus the neutrons of a particular element. So if you think about it, if something has a different mass number but the same number of protons, then they must have a different number of neutrons. Take, for example, hydrogen here at the bottom. We have three different isotopes of hydrogen. Now this first one is ordinary hydrogen, just typical hydrogen. It has one proton and no neutrons, which means its mass number is 1. As you can see down here, the notation that we use is the symbol for hydrogen. We put its atomic number in the lower left-hand corner and its mass number in the upper left-hand corner. Now for the heavy hydrogen, it has one proton, which makes it hydrogen, and one neutron, which makes it a mass number of 2. So as you can see, the mass number is 2 down here, where it was 1 of the previous example. Now this last one is known as tritium, tritium, get it? One proton, making it hydrogen, 2 neutrons makes it 3 for a mass number, but it still maintains the 1 electron. In each one of these examples, 1 electron because it's a neutral atom of hydrogen. So in summary, isotopes are the same element, which means that they have the same number of protons, but they differ in their number of neutrons. Add neutrons, they become heavier, but they maintain the same identity. They're all hydrogen. Many substances have multiple isotopes, and you might be asking yourself, well, how are isotopes made? Well, that's a great question too. Isotopes just occur naturally when an element is made in the belly of a star or at supernova when a star dies, collapses, and spits out its matter into the far reaches of the galaxy and the far reaches of the universe. Isotopes just get made. They just exist. But they exist in different natural percent abundances as we find them on Earth. And those percent abundances are known values that scientists have calculated, and we can determine the percent abundance of each isotope. Say, for example, chlorine. We know that there are 2 common isotopes of chlorine. 25% of chlorine is one isotope, and 75% of the chlorine is a different isotope. And we know this. This is true of all elements. And you can look up vast data tables of different elements and their different abundances of their isotopes. One isotope of a particular element tends to be more common than any of the other isotopes, but it is possible for an element to have 2, 3, 4, 5, or even 7 different isotopes based on the number of neutrons in the nucleus. And it's important to note that if we're ever talking about 2 different isotopes of the same substance, in this case hydrogen, we name them based on their mass, because you can't name them based on their atomic number because they're both hydrogen. So you'd say, well, this one has 1 proton and this one has 1 proton. But if you're ever comparing 2 isotopes, or in this case 3 isotopes of one particular element, we name them based on their mass number. So this first one is called hydrogen 1, this next one is called hydrogen 2, and this last one is called hydrogen 3. 1, 2, and 3 for their mass numbers of 1, 2, and 3. Now all of that discussion about isotopes and percent abundances leads us to this atomic mass. What is atomic mass? Well, atomic mass is the weighted average of the isotope masses of an element naturally occurring on Earth. So if you take a sample of, say, carbon, for example, most of the carbon is going to exist as one isotope, where there might be 2 or 3 other isotopes of carbon that exist in that sample, but a majority of it will be one isotope. And what scientists do is they take the mass of the isotope, multiply by its percent abundance, and add up those numbers to determine the average atomic mass, or just what is known as atomic mass. So if you look at a square on the periodic table, the number in the top, which represents the number of protons, is the atomic number. In this case, carbon has 6 protons. Its symbol's in the middle. Sometimes it includes the name. In this case, we don't include the name. But this number on the bottom, which is usually a decimal, is the atomic mass, which is a weighted average calculated using percent abundance data. And you will always be given the percent abundance data or be given the means to find the percent abundance data. So you don't ever have to worry about guessing at what isotope is more abundant. But what you'll do notice is that the average is closest to the most abundant isotope of that element. So let's say, for example, we look at carbon and we know that its average is 12.011. Well, that's almost rounded very close to 12. And we can judge that carbon 12, or mass number of 12, is the most abundant isotope of that particular element, in this case, carbon. And generally speaking, if you take that atomic mass, which is in each square of the elements of the periodic table, and round it to the nearest whole number, you will find the most common isotope of that element. Now let's quickly show you how we calculate that average atomic mass by using the mass values of a particular isotope, in this case chlorine, and their percent abundance values. Now it is known throughout science, and we would tell this to you, as I mentioned before, that these two isotopes of chlorine basically represent all of the chlorine naturally known on Earth. And the smaller one is the more abundant. This is 75% abundant, and the other isotope, chlorine 37, is 25% abundant. So let's take mass of 35 multiplied by 0.75, which is the percent abundance in decimal form, and we'll get 26.25. Now we need to do the same thing for the other isotope. We'll take the mass of chlorine, which is 37, multiplied by its percent abundance, which is 0.25, and we'll get a value of 9.25. Now what we do is we take these two numbers and we stack them up and we add them together. And if you take 26.25 plus 9.25, you'll get 35.50. And if you look on the periodic table, the average atomic mass, or the atomic mass of chlorine, is 35.45, which is pretty close to what we just calculated here when we use the percent abundance data. Now, the reason it's different is because I just use nice round numbers for these percent abundances, but it's not exactly a 75-25 split. It's a little bit off, but now you know the process and how to calculate a percent abundance. Now with this last example, I'm just going to let you try it in your notes, but it's the same process. We've got three isotopes of carbon, carbon 12, carbon 13, and carbon 14. And you can take the mass times its percent as a decimal, and then the mass times its percent as a decimal, and even this one times its percent, but it's such a small percent that it's essentially zero. So really you're just adding up two isotopes. But if you take their mass times percent plus mass times percent and then add them up, you should get a number that is close to 12.011. Well, that takes care of this video lesson. Thanks for watching.